Started for today, and for better or worse, this is our last one on optics. So I guess the sad news is we are not going to do optics anymore. The good news is we're going to go into a new topic. And so I used to say of the three classes I teach, I like the 122 the best, but I don't know. I was thinking about it this morning going, I don't know, maybe that's changing. I kind of like the changing of the topics and going from different topics, and so that's about what's going to happen again here. And so we are going to finish up optics here today, and as I mentioned before, just see how far we get, and that will just be the end of it. But as I looked over the material, I was actually quite surprised that we're actually going to get pretty far. So here's kind of the game plan, and you might want to make a note of it. If we don't get this far, then I'll mention that at the end here. But chapter 38 includes three things. It includes the diffraction gradient and the multiple slits, the stuff we talked about on Tuesday. And so we already covered that, although I do want to review it a little bit because it will really help us on what I think is the hardest one to kind of comprehend. Although fortunately the results is actually pretty easy. So that's mostly what we'll focus on, is the results, not so much the derivation of it. But we do need to spend some time on diffraction and what is diffraction, which, by the way, is the spreading out of light. And then finally to polarization, a topic that may be actually a little new to you, and hopefully it'll make sense. It's not real complicated, but since our human eyes do not pick up the polarization of light, it's an optical property that we as humans aren't as familiar with. When we say bright, dark, and we say red, green, and blue, our eyes have picked that up. So I can talk to anybody on the, outside of a physics class and tell them about, hey, here's some colors, and here's bright, and here's dark, and they kind of get all that because your eyes pick it up. But polarization is an optical properties that human eyes have not adapted for in any way, used a lot with technology and information, but again, not, and probably is the future of microprocessors. Once we get away from these crazy bits of electronics and get to an optical processor, then it probably will be done with polarization. Who knows what will be the first, polarization, or maybe the spin of the electron, or maybe some other quantum effect. Anyways, but I digress here. I just wanted to point out that that's where we're going to go. So I think we are going to get to polarization, and I'm glad we are. Although your author goes through different ways of polarizing the light, and that's what we won't have time to do, as you'll see. We'll just have enough time to say, what is polarization? And I'll show you the most common form of polarization, and then your author kind of just real quickly lists three others, four, if you call optical activity in there, and he just kind of brushes them off. So anyways, point is, I think we'll do really well and almost get done here with chapter 8 here. So let's go to the second option here, diffraction. What is diffraction? And I think the best way to introduce diffraction is, first of all, say diffraction is the spreading out of a wave when it goes through a single opening. Okay, now I got the laser set up to show you that in just a second here, but before I even begin there, it's really important that you remember what we did with the double slit, because I am going to use the double slit as an analogy to hopefully get you to understand in a compressed way the single slit and the complications of a single slit, because we've been ignoring them so far here. See, what we have done is we have said that when the light goes through a single slit, the energy spreads out equally and uniform in all directions. And it was Max, you who brought that up and said, that's not what I see on that screen. And you're right. You don't see that on the screen. So we need to add something to our double slit. One more piece to this double slit, and that is diffraction here. So, putting diffraction away for just a second here, you might remember that as we spent the last week and the last lecture analyzing this, what we did here is we said, all right, let's look at the intensity at some point on the screen there. And what we said is we said there would be some light that comes from that opening and light that comes from that opening, and they would differ by a path length of d sine theta, where d is the distance between them. We got this distance by doing a little trigonometry with this triangle and said, all right, that is the extra distance that the lower beam travels compared to the upper beam. And that's why then when we get to this point and we go to calculate the total electric field at that point, we take the electric field that is generated from the first wave and we added it to the electric field. We used a minus here. We added it to the electric field of the second wave. And we said it was this extra path difference, delta is to lambda, as phi is to 2 pi. That is, this extra distance is what contributes to an extra phase between the two. And we argued that if this phase was 2 pi, 4 pi, 6 pi, or put another way, if the distance was 1 wavelength, 2 wavelengths, 3 wavelengths, we argued that they would add up constructively. Fair enough? And I hope you remember that. And then we did a bunch of math. We added these together, we did a trig identity, and we came up with this, that the intensity at some point over here on the screen would be equal to the intensity at the center of the screen, and then it would go from being bright at the center and then go weaker, 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 weaker until it got dark. Then it would get brighter, 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 brighter until it got bright again, all the way, constructive interference, then it would taper off again. And you would have this cosine squared based upon the phase angle between those two waves. And that phase angle is contributed from the distance between them. And so that phase became 2 pi lambda d sine theta. All right, if you can keep all of that in mind, then let's reanalyze in a little more careful detail the single slit. Yeah. Well, this delta, okay, is the path difference between the two beams. You're good with that, you said. Okay, now, that path difference would be like a half a wavelength, maybe 3/4 of a wavelength, but it's some percentage of a wave, right? It could even be more than 100%, right? This could be 3 waves. All right. But if I wanted to know how many waves fit into this space, I would take the distance and divide it by the wavelength. All right. And so that's how many actual wavelengths. And I claim that is proportional to, in other words, distance, how much distance I have compared to 1 wavelength would be the same as how much the phase of the second wave is to 2 pi. Because 2 pi represents a whole wave. So this is the physical distance. This is the mathematical equivalent in terms of phases. And so that helps me work out how does the phase between the two waves correlate to actual distance. That's really what I would want to know. In fact, you saw this equation put together so that it looked like this. You substituted it in, and you had pi times d times sine of theta over lambda. In fact, you even went one more step, and we replaced sine theta with the distance up the screen divided by the distance to the screen. And that's probably a more useful form when you go to solve a homework problem or you go to study what's going on the screen, because this is telling you the intensity at a position y on the screen, which is based upon the distance between the two slits, the wavelength you are using, and the distance to the screen. So it puts all those together. But it's all of these together that contribute to why the second wave is at a phase. So mathematically, I really like this. And those of you who are perhaps math majors, you probably like this form. This is neat. But physically, it's not very useful because it's phi. It's the phase between the two waves. And well, what's that? And there's not, you know, it's a phase between the two waves. And the physicist in me, and especially the experimental physicist in me, says, look, there's got to be something physical here. Well, why is there? And so I like to, you know, and ultimately there is. There's a replacement of physical position, distance on the screen, distance to the screen, distance between the slits, size of the distance between the two slits. All right, now, like I said, I probably shouldn't dwell on this too much because I know we covered this, but at the same time, if you didn't really understand what I did with the double slit, my analogy I'm about to do will not help you because I want to compare what I did for the double slit to what we are about to do for the single slit. In fact, I'll just kind of move this off to the side so you guys can see better until we need it, which is, this is for polarization, so we won't need it till the second hour here. All right, so now let's do this. And that's what this diagram up here is for. Let's look a little closer at a single slit. And probably the best place to begin is really with a physical experiment. Let me close this door so we can get pretty dark in here because this one gets a little bit hard to see. In fact, I'll even power down the display here so it gets even darker. And then when I turn down the lights here, all right, and turn on the laser beam, and some of you already saw as you were coming in, I was playing with this laser beam in the sense I was trying to shine it through a small slit, a small opening. And this one is adjustable. Let me actually see if I can open the slit and see if you can see a dot. I'm tempted to move the slit out of the way so you won't see the diffraction already, but maybe I better not. But right now, maybe, do I dare? Yeah, I think I can find it in the dark. Let's see. I'm going to just put the laser beam. So there is the straight laser beam. All right, when it's not shining through a slit, and hopefully not a surprise. You know, it's kind of this round circle. All right, but if I move the slit back here and shine it in here, you will mostly see the light going right at the center. But you will see this huge spread. And that's what we said at the start of the last chapter was the requirement of going through a hole. In order for the light to illuminate the whole screen, for this double slit to work, I had to demonstrate to you that the light will spread out when it goes through a hole. But as I said, I'm not going to try to explain it to you till now. And so that's what this first hour is about, trying to explain it spreading out. And so I want you to see it. In fact, what I really want you to see is, what do you think might happen if I close up the hole? And I want you to see, and it's pretty dark here. Can you see bright and dark fringes off to the side? Yeah. All right. And so we haven't really talked about this, and I want to emphasize, this laser beam is not going through a double slit. This laser beam is going through a single slit. So our assumption that the light would go through this single slit and spread out equally in all directions is very wrong. You can see that. You can see that the center part is certainly spreading out. But then it goes dark, bright, dark, bright, dark, bright, dark, bright, dark, bright. So you can see my justification by saying the light definitely spreads out left and right. But for me to say that the light spreads equally left and right is just wrong. And so this is the last piece we need to add to our double slit. We need to say, not only do we have a double slit, and not only do we have the interference from the two slits, but we got something more complicated going on in the single slit as the light goes through a small opening. Watch, I'll even close it up more. What are you noticing? And particularly the center one, what are you seeing? Yeah, see how it spreads out more and more? And I'll stop right there for a moment. But again, I want you to notice that as the light goes through this single slit, as I'm closing up the slit, as I am making the slit smaller and smaller and smaller. And so now you're going to see where we're headed here. We're going to make the slit infinitely small here in a second. But as the slit gets smaller and smaller and smaller, the light really does spread out kind of uniform. And it hasn't got there yet. The center one is spread out, you know, maybe, looks like I got about 8 centimeters here on the screen. And these other ones have spread out. And there's still a little bit of dark between them, but they are spreading out too. And then, hopefully, not too much of a surprise, that in the limit of this thing getting smaller and smaller and smaller and smaller, and this will only go so far before reflections take over. Yeah, nothing like welcoming you to class, huh? What a start of your day. All right. And so right about here might be the best I'm going to get it. No, maybe a little more. About there. You'll see that the light does seem to spread out equally in all directions. So our beginning assumption that the light spreads out equal in all directions is validated only if our slit is really small. But if it's not extremely small, then something more complex is going on. And like I said, that's this diffraction that we want to study here in this first hour. And so I want to go a little bit more. I'm kind of curious what we can see, but I think at some point, yeah, I get the limit of my machine there. There we go. And so right about there. And I think it would actually spread out more if it wasn't for the fact I'm going through a tube, and the tube is actually blocking it a little bit. You'll see it here when I turn the lights back on, if I can even find the switch. Ah, there we go. But my laser beam goes through this slit here, and then as it spreads out, I've got a tube for it. You can see I stole this out of that the spectrometer that we used in class.
Turn the tube around and fire the fire laser into the tube at the end of it.
Funny you asked that. I was just thinking the same, and I might be able to see it spread out more. The reason I didn't is because it's difficult to line it with the slit that way, because I can't see where it's hitting. So going this direction, I can see where it hits the slit. But when it goes this way, I kind of block the spreading. If I turn it around, you could probably see it. But I'm not going to mess with it because I think it'll probably take me a couple minutes to align it, and not good use of our time. I really want to make sure you understand this single slit. And then we have enough time to get to my polarization here. So, like I said, I wanted you just to see the experiment here at first, because now, if we turn some light back on here, we can then begin to ask this question. Obviously, the pattern we see does spread out the light. But also, obviously, how much or how little it spreads obviously depend upon the size of that slit. Keeping in mind that as it got infinitely small, it was spreading out uniformly. So, let me emphasize what we've done so far so that you don't miss this, because the author spends so much time, and I too, spent so much time talking about the double slit, it's almost as if we were done with the double slit, and we're not. I want to go back and add to that. And here's what I want to add. What I want to add is the fact that what we've done so far is we said when the light came through this double slit, it spread out uniformly in all directions. And you can see that that would only be true and be valid if the slit was really, really small. And so let's take this next step and say, well, what if it is not really, really small? What if the slit has some size? Now, it's got to be reasonably small. As you can see, you don't notice any spreading of the light until you get close to the wavelength. And when we get like, 1/100th of the wavelength in size, then it spreads out uniformly in all directions. But somewhere in between there's an interesting spread and a pattern that you saw: bright, dark, bright, dark, bright, dark. And I claim we can explain that in terms of interference. Here's the idea. Here is Huygens' idea. He says, look at a double slit. Look at a single slit for a moment. And he says, ultimately, we're going to put a double slit, but ignore the double slit for a moment. Let's just take an opening. And so we have something to work with. Let's say that the opening is size A. All right, now keep in mind, D is the distance between the two slits. A is the opening or the size of one of those slits, because eventually we're going to have two slits. So obviously, A is going to have to be smaller than D. You can't have the opening bigger than the distance between them. Otherwise, you don't have anything in between them anymore. Okay? And you have one big opening. All right. So there's my opening with A smaller than D. And that's going to become an important role here. But more importantly for you guys, I just want to remind you in the equation that we're going to have A's and D's. And don't confuse the two, because I've seen students really confuse it. And you'll see why. It's really easy to confuse them. But nonetheless, here comes the light. And so as your author has in this picture, here comes the light. And here's what he says we're going to do. As the light comes in, instead of thinking of this as one big opening, why don't we think of it as millions, if not billions, if not trillions of little tiny slits? Because what do we know about little tiny slits? How does the light spread out from a little tiny slit? Yeah, equal in all directions. So we're going to do exactly what we did before. We are going to say, like we did with the double slit, that the light spreads out equally in all directions. And now it wasn't really true for the double slit, but it would be true in the limit as that slit gets smaller and smaller and smaller. And so if I stand over here and I ask, what are you going to see straight down the middle? What are you going to see at some distance above where you are now looking at some angle theta up on the screen? And so again, just like we did for the double slit, let's talk about a distance y up the screen, or let's talk about an angle of theta. And here's the logic. And I think you can see it in this picture, although that picture's a little bit further along than I want you to see. In his diagram, he shows 5 different rays. I've got, I guess, more than that, but I better not try to draw all those. That'll get kind of complicated. But I do want you to see that one of the rays would be coming from this edge, and it would hit here. There would be a second, a third, a fourth, a fifth, a sixth. And to do this technically correct, there would be an infinite number before I got to the last one. Okay, and so I get to this last one. This last one would shoot on up there. And if I kind of draw the same picture that, again, we saw back here with the double slit, there would be a path difference between the two. Now, remember, when I say there's a path difference between the two, I'm talking about the path difference between the ray at this edge of the opening and this ray of the opening. But the geometry would still be the same. This part would be the size of the opening A, so sine theta is the path difference between the two. Also remember, this is the path difference between the two. Here's why I say that. Because what if this distance? What if the distance, which is A sine theta, is an integer number of wavelengths? What's going to happen on the screen? And we are going to see something different here. What happened back here with the double slit? What did we say here, back here when we did the double slit? When we said d sine theta is an integer number of wavelengths, what did we say happened on the screen? Yeah, we said this is the places where you would get your bright fringe. Fair enough? This is where it would be bright. And we made that argument because this wave and this wave would be one wavelength or two wavelengths. They'd be in phase, right? Be careful here. Because when I write this on the board, you're going to say, oh, well, it's going to be a maximum. No. Unfortunately, no. And I want you to see the difference. So hopefully you won't confuse it as you are working out the problem. What's different in the single slit analysis compared to the double slit analysis is the following. This only has two beams. How many beams do I have here? An infinite. So really what you have just told me is the first and the last are in phase. Okay, but what about all the others? That's the key. What about all the others? I can't tell you the result on the screen quite yet until I look at all the others. Whereas the double slit, all the others were done. We just had two. In fact, we even did a 3 and a 4 slit, so we're going to look at that again too, since that's going to get us a little bit closer to analyzing a multiple, in this case, an infinite number of multiple openings. But here's what your author does. And that's why his picture up here looks a little bit different than my picture. He says, okay, the whole path difference, and what he means by the whole path difference between the first and the last is this. But what about halfway between? What about this middle ray? What would be the path difference? And again, let's just say this is an integer number of wavelengths. In fact, let me make it simple. Let's just say this length right here is one wave. One wavelength. So how is this one and the first one comparing? Half. So what happens to these two? Okay, so these two are destructive. Now again, by itself, that doesn't help me because that's only two of the waves. I've got to add all of the waves. So it doesn't do me any good to look at the first and the last or the first and the middle, but all of them. But here's the key to the understanding here. The first one and the middle one, as you just said, would add up destructively. How about the one that is microscopically below the first one and the one that is microscopically below the middle one? Those two would be a half a wavelength. How about the next one, which is a microscopic below that one and microscopic below that one? How do they add up? Destructive. So what's going to happen when I add up all of these in pairs? Destructive. So what does this condition give me? This right here gives me minimums. Or if you like, it gives me the locations of the darks. Did you catch that? I mean, I'll draw your attention back to the experiment. I won't shut the lights off again. But do you remember seeing bright, dark, bright, dark, bright, dark fringes, even though I was going through a single slit? But what's interesting here is this equation, A sine theta equaling an integer number of wavelengths, is how I would then figure out where the dark spots are for a single slit. But over here, and I guess I didn't put it on, well, I put it on the board here. D sine theta, being an integer of number of wavelengths, gives me what? The maximum, gives me where bright spots are. Now you can see ultimately we got to put this together with this, because when we actually do go through a double slit, we are of course also going through a single slit. A single slit twice would be, of course, how we have to analyze this. And so we got to put it together. And that's why we're doing this first step. This first step is saying you will get bright, dark, bright, dark, bright, dark, bright, dark patterns. In fact, the next picture is a good one to look at here, as your author said, if you were to plot this intensity, it'll probably look something like this. And again, drawing your attention back to what I did earlier, isn't that kind of what we saw? Didn't we see down the middle really bright? And as we went to the left or to the right, as we tapered off, it got weaker and weaker and weaker and weaker, and eventually got dark. And then it got bright again. And then it got dark. And then it got bright. And then it got dark. And then it got bright. And so we got a lot more analysis to do in order to figure out what the intensity pattern is for a single slit. But again, using the double slit as a guiding principle, here's what we did last chapter. We said, give me the equations of where I would find the bright ones and where I would find the dark ones. And so we got the bright ones when d sine theta was an integer number of wavelengths. We got the dark ones, or the dark positions, when it was an integer and a half wavelengths. Of course, and then we argued it could be something in between, and that's when we went through this more complicated analysis to figure out what would be the equation, and we saw that it had a cosine squared pattern to it, going bright, dark, bright, dark, bright, dark, bright, dark. And I'm about to do the same thing. And so far, I've done this much. I haven't done this quite yet. But what I have done is I have said, where would you find the dark spots? And halfway in between, and maybe I should be a little careful, it won't be exactly halfway in between. So maybe I should say approximately. Since there's not just two beams, you can't really say it's going to be in the half. And it turned out it's not really halfway. But it's reasonably close to the half, so I'll just put that on here. But again, just want to emphasize, we've done half the problem so far, right? We've done the same half that we did back in the last chapter as we analyzed the double slit. We said, where would the brightest parts be and where would the dark spots be? And this is what we have. And again, just want to emphasize then, notice this equation. This equation gives you the location of the dark spots. Because it looks a lot like this equation. It's why earlier I was saying don't confuse the A and the D. You got to recognize the D. That this has to do with a interference from the double slits. And this is where you would get bright spots because of the interference from the double slits. But this one here, notice the A. And this is saying you get the interference from all the infinite number of rays that make up within the single slit. And so this equation gives us the minimums, and this equation gives us the maximums. All right? So, if that much made sense, let's continue on here. Let's look again at what we did with the double slit. We first said this is the locations of them. And now we said let's get a more exact equation, one that would tell us the intensity pattern. One that would give us the equation of how it went bright, dark, bright, dark. And as I said last time, this wasn't complete because when we analyzed this double slit, we said the light spread out uniform. So, how does the light actually spread out? What does that equation look like? Well, as I said, it should be this complicated equation. Really bright in the center, tapering off, getting bright again, going dark, getting bright again. But notice that each time it gets brighter, it's not as bright as the one before it. And so we do have a fringe pattern, bright, dark, bright, dark, bright, dark. But we also have a dimming effect as we go further and further out. And how do we get that equation? Ooh, that's a little harder, as you could expect. We have to add up an infinite number of waves. This was nice. We only added up 2 waves. How do you add up an infinite number? Well, let me start with what you saw last time. Let me go back to our flash page here. Oh yeah. Department, there we go. All right, flash. Now, if you remember, at the end of last lecture, we looked at this. And we said, let's do the gradient. And what we did with the gradient is what we were really saying here is, how could we add two waves together? Now again, I mentioned that we did a trig identity in class. But what we could have done is we could have drawn them as little arrowheads, what we call phasors. So, giving me a chance to clean up the board here, and oh good, I'll leave this here. This is for the double slit. Let me kind of clean this up a little bit. But even though in class we got this equation by using a trig identity, let me emphasize of what we're trying to show over there. We're trying to show that if you represent the intensity of the first wave, or I should say the electric field from the first wave, as a little arrowhead, and that's that top one up there, and you let the second one be represented with the same intensity, but maybe out of phase with the first one, then this drawn across here is what we call the total electric field, the sum of the two. And again, just kind of reviewing of what we did last time, we said this would be the picture of straight down the middle. And if you had two openings, well, then you would just add two arrowheads together. But if you had three openings, you would have to have three arrowheads together. And if you had four, you'd have to, and you get the whole idea. And if you have an infinite number, you would have to have an infinite number of arrowheads. And so as I try to figure out what is the sum of an infinite number of waves, let me not try to use trigonometry to do that. Let me try to use geometry. Let me draw some arrowheads. And so that's the advantage here of looking at these phasors. If I were to draw an infinite number of infinitely small phasors, I'll stop there, since it will take an infinite amount of time to draw an infinite number of phasors, right? But you see the idea that I would have this long chain. Actually, let me go a little bit longer so I can get some arc to it that I want you to see here. So let's do a little bit longer. But that would be what my picture would look like if it was straight through. And so all of these kind of look the same as straight through. Now, of course, when I'm doing the single slit here, my slit gets infinitely thin. So that's why I would say these vectors would have to be infinitely short, but an infinite number of them. And so this would have a certain length. I'll call it E. I don't want to use the E naught because I have it over there. Any suggestions? E.
Infinite.
Down the middle. Center. E initial. All right. I like it, I guess that. Initial. Down the center. Yeah.
Isn't there a finite number of rays that go through there?
No. I can make it infinitely small, can I?
No.
No, why not?
Because you can't do that.
Because why?
Because the universe is quantized.
Oh, okay, forgetting that. All right. So, all right. So, there's. Actually, I'm glad you brought that up because that's exactly the next lesson we're going to go to. Is that starting in about 1900, quantum mechanics starts kicking in. But let me just say that I could at least make it, say, maybe a billionth of a billionth of a billionth. How's that?
Sure.
Okay, but extremely small. So we're still doing what I call classical physics here, yeah. And then when we learn about the next step and the next discovery, which I know this is going to be disheartening a little bit, but I know you've done a lot of work, and I know it seems hard, right? But we're still in the 1800s. I mean, none of this, I mean, all of this was done in the late 1800s here, right? All of our optics, all of our thermodynamics, so we're eventually going to get to 1900. We're almost there. The first chapter on Monday. We will talk about what Einstein did in 1905. All right. So we will only be 107 years behind the latest science. So obviously there's a lot more to learn here. So that's, my joking. If it makes you feel any better, also remember this. Even today, you know far more than Newton ever did. You're all smarter than Newton. Try that one, right? Right? I mean, Newton had calculus. Calc 1. You took Calc 1 before you even started this class, right? He had mechanics. He had none of this, right? So, you're all more educated than Newton, but you're also 107 years less educated than you need to be. So, more to come, yeah.
Dividing is up to infinite number of times, it's infinitely small. Like the wavelength itself might the wavelength itself might interfere in.
Right.
But well, I mean, okay, let's just say that we divide it enough times that it's like considered infinite.
Right. So, all right. So I'm going to take it smaller and smaller and smaller. And as we will point out, when science tried to take this smaller and smaller and smaller, they discovered something new called quantum mechanics that we're going to discover. But we're taking the point of view that we're still in classical physics, and when science actually tries to make it smaller and smaller, they see that the analysis that I'm about to do doesn't work. That's why they know something more is going on. And so again, we'll talk about that. But for us today, let's just take it infinitely small. All right, so now back to this notation. I'll just call this EI. Eventually it'll go away, but that would be straight down. And that's the picture I want you to see. This is what we did last time. We said that you have a bunch of rays going straight down. If you were to move off center a little bit, okay? And so I don't know if you caught this last time, but this is the screen location. So if I were to move over a little bit, that means, and if we go back up to the double slit, they're slightly out of phase. That is kind of what this diagram is. Two that are out of phase. If I drew three of them, I would be looking like that picture, where it would look like this, and look like that. And then the resultant would be there. And of course, what I was trying to show you for the gradient was a neat property that as you have more openings, so when you compare the 2 to the 3 to the 4, this curls around and can get to 0 in a much shorter distance on the screen. In fact, we keep going here, and if I go too far, I'm going to lose the picture I want you to see, but this is what we did last time. That you would only have to go so that each of the individual waves are 90 degrees out of phase for the quadruple slit before they canceled off. You wouldn't quite get that for the triple slit, and you're not even close back on the double slit. The double slit has only dropped its intensity to a half, but the quadruple slit has already gone to 0. So the property was that the more openings we have, the more complicated this interference can be. And in this case, we have a beam that narrows up. Now, that's what we saw last time. But what I want you to see now is kind of back here in this step here, when this vector that is this phasors that is made out of 4 pieces has curled up. What would that look like for something here where I'm trying to add an infinite number?
Even when the slightest change in V or theta, it just curls so much.
Yeah, it won't take long before it curls all the way up and gives me a 0. But it does begin to curl. But an important property here is, even though it's curled up like a part of a circle, and eventually it's going to make a full circle and go to 0, and that's why I'm going to get a dark spot real soon here. Okay. But at this point, I have not moved over far enough on the screen till I got to a dark spot. But I do want you to see this arc would be the same length as this one, right? I still got the same vectors in there. Just like that plus that was what it was when it was laid straight. Because what I would say right now then, and if I do a little geometry, I've got a part of a circle. It kind of looks like the center of the circle might be right about here. No. Maybe here? No, here? No, here? All right, well, that's going to have to do. All right. So somewhere over there would be the center of the circle. And so there would be some radius, let me call it R. But again, if the analogy keeps working for you, there would be some phase angle between each one. And let me just focus on the phase angle between the last one and the first one for a moment. Because isn't that what I did back here? I mean, let me draw it in the picture. The first one is drawn horizontally. So this last one, this would be some phase angle between the first one and the last one. Let me call it beta for just a second, which I should check. I think that's what your author calls it. Yeah. So he calls this between the first and the last one beta. All right. Now, maybe I should come back over to here because, again, this is the real physical picture. And I don't want you to miss it over here. But this is what we would call a phasor diagram. This is a geometric way of adding up an infinite number of trig functions. Okay, and I don't want to add up an infinite number, although I guess I could write them as trig functions, take the limit, and then I'd have to take an integral of some trig functions. All right, but I think the geometry here is a lot easier here, and so that's my approach there. And so again, want to just say that beta represents the phase between the first and the last. So if I come over to here and do kind of the same proportionality that we did for the double slit, I could say phase difference is to lambda as beta is to 2 pi. Right? And again, this is this extra phase of the last wave compared to its wavelength is how much phase compared to 2 pi. All right? Which of course means that beta, the phase between the first and the last ray, would be 2 pi lambda times delta. Now this delta is a sine theta. So again, noticing the same pattern mathematically that we saw for the double slit. Now granted, a little more complicated because we don't just have two, but when I'm looking at this, it looks exactly the same because I'm only looking at two. I'm looking at the first and the last. Now, how does this geometry help me? Well, here's why. If I wanted to know the resulting electric field from this infinite sum, what would it look like in this picture? I've added an infinite number, and maybe it would help in this picture here, or this picture here. Isn't the sum of all of those waves an arrowhead from the beginning of the first to the tip of the last, right? And so in that picture it's blue, so I will do it in blue. And so this is the resulting electric field. How about I call it ER, the resultant electric field. Okay? So the arc length is EI. When you draw across a circle, that's called a chord, right? So the chord is ER. In fact, why don't I just make a triangle out of this? If I look closely at this angle here, And maybe I should draw it a little more detail over here. But if I had an arc here, and I were to draw back into this circle here, okay, and I have, well, I didn't draw my drawing very well. Bummer. Shoot. But this first one, if I'm going to draw it level, doesn't the radius have to be straight up? Because I've got to draw the radius perpendicular. I should have caught that earlier on. So maybe I could improve my drawing a little bit. So maybe I curved it too much. But I should be saying that this radius needs to go straight up. And then this picture's not a very good picture either, because I wanted to make the radius straight up, the circle arc come over to here somewhere. But the point being, if I take these two horizontal lines and I look at this, tangential there, maybe something like this and something like this, I hope you're seeing that that angle here would be the same as that angle. Fair enough? Those are two parallel lines. Those are corresponding angles. I will also say, since I'm going to draw this horizontal, that's 90 degrees. So this angle in here is actually this angle and 90 degrees, which is that angle. That's a long way of saying, isn't this angle out here beta? So what's this angle? Yeah, that's beta also, exactly. So this is beta 2. And that's really what I want to get at, because again, we're going to do some geometry. And do some geometry, I need to know some angles. And so I'm claiming that this angle here is beta. Okay? Because that, and then 90, and then 90, and added together are beta, and those two added together are beta.
Is the angle between ER and EI the supplement of beta?
Between which one?
ER and
Oh.
EI?
Ooh,
It looks like it in the picture, but it could just be the picture.
supplement. I don't think so.
Okay.
But it might. But I'm not even going to go that direction. What I want to do now is, if all that made sense to you, then you're going to be pleasantly surprised how easy the rest is, and pleasantly surprised how easily we get a very complicated equation. Let me get rid of this and come back to what we are even after here. Remember, I'm trying to show you that if I were to add all of these waves coming through the single slit, they would interfere with themselves. And so I add an infinite number, and I will get a structure or a pattern based on the interference. So a simple way of describing diffraction is to say diffraction is like the double slit where you have interference. You just have interference within the slit itself. There's an infinite number of waves to add up. And that's what I'm trying to show you, that I can add up an infinite number. And surprisingly, it's pretty easy in geometry to do phasors than it is with the trigonometry and the calculus. So that's why I chose this approach. That, and also, I think it's a good idea that you just kind of be exposed to phasors a little bit. Your author doesn't do too much with them. It really is considered a topic past this level and on to the next level. But at the same time, I have seen many students who, in their upper division come back and they just walk into UCSB you know, and the teacher either didn't explain phasors really well or just assumed the students already got phasors, and that's really not true. This book doesn't do it too much, but we do it a little bit. We do it more so in Physics 122, for those of you who had 122, and we do it more so in electronics, for those of you who had electronics. So between what a little bit I do here, what little we do in 122, and hopefully what lot you do in your electronics, you get a lot of exposure to it. But like I said, let's finish this up here. And so here's what I would do. I would say then, if that's beta down the middle, then this angle would be beta over 2. And if I look at the sine of beta over 2, then I look at this triangle here, then the sine of beta over 2 would be this leg, which I would call ER divided by 2. Fair enough? Over what leg? Well, R. Well, that's supposed to be a subscript. ER over R. So that's a subscript, that's not. Okay? But let me also say this. How do you get an arc length? Yeah, S equals to theta R. So using that here, let's see what I would have. The arc length would be this EI that we talked about. It would be the length of all of them added together when they were in a straight line down the center. And the arc of this whole thing is beta, and then the radius. And why that's nice is maybe I can get rid of my radius out of this equation. I can put these two equations together. And so I will. I will write this as sine of beta over 2 equals, and I'll write this as ER over 2 still. But when I replace it with my R, I get an E naught over a beta. Now, again, why am I doing this? Well, what am I trying to get? Well, the intensity pattern.
Is it small enough to equate beta with sine of beta?
No, because this I would not call beta a small angle by any means. Look at this picture. I mean, beta is more than 90 degrees. Right, yeah. So I'm not going to do a small angle approximation. That would limit me to just, very, very small physical angles. But remember, beta is not the angle that the light is spreading. I would say the angle that the light is spreading is small. That's our theta. Theta is small. But the phase between the waves is not small. One whole wavelength would be a whole 2 pi of phase. Yeah. So not going to do a small angle approximation, but good guess here. I'm just going to square this because, like I said, the idea is to get the intensity. And what did we say the intensity was equal to or related to? The square of the amplitude. Okay? And so if I were to square this, wouldn't I have the resulting electric field squared? And I'd also have this down here, so we'll talk more about that. But watch what happens when I square it. I get sine squared beta over 2. And over here, I get ER squared. I get E naught squared. I also get, if I can write it this way, if I can write it by putting the beta on top squared and the 2 on the bottom squared, right? So I wanted to look at the electric field separately because what would you call these electric fields? This would be the intensity that I'm looking for. What is the resulting intensity? It's the electric field squared. What would I call this? Yeah, the intensity down the center, just like we did for the double slit. So that ratio must be equal to sine squared beta over 2 divided by, and I'm just going to bring this over. And in fact, so that they look identical, I'll put the beta over 2. And so the result that we get, and maybe I can clear this up now. but maybe I'll leave this equation down here at the bottom. The result we get, and like I said, maybe pretty surprising, is I have an equation for the intensity. The intensity then is I naught times sine squared beta over 2 over beta over 2 squared.
Why are you dropping the square from the field to the intensity?
The electric field squared, or the amplitude squared, and I guess last chapter I did it this way. I said, let's go back to sound waves. Let's go all the way back to chapter 17. What was the intensity for sound waves? We said it was the density of the sound times the velocity times the frequency squared, both of which, none of those I'm really interested in. What's the next one? Amplitude squared. So the intensity is related to the amplitude squared. All right, with that in mind, as we take that to our light waves, if I calculate the electric field, that's the amplitude. So to get intensity, I got to square it. Yeah. So E squared becomes... The truth is, there's probably a bunch of numbers here, but there's a bunch of numbers down there and they cancel off. So the numbers that I'm leaving off show up on top and bottom. Right. Right. But we got it. Do you see we just added an infinite number of electric fields now? And we are saying that the intensity should look like this. Now, let me compare it with the double slit. And so maybe I should put single slit is the equation we just derived right here. The double slit is what we're using as an analogy. And in fact, maybe I should write it in a form that had the phase in it. See how that looks like that? Almost. It does have something downstairs that we better talk about. It's got some interesting effects that we don't see for the double slit. So it is more complicated, I agree. Even the derivation was more complicated, I agree. We're adding up an infinite number of pieces. But what I want you to see is, first of all, is notice it is a trig function squared. So just like the double slit, the single slit is going to have the same bright, dark, bright, dark, bright, dark, bright, dark pattern. And isn't that what you saw a half hour ago when I shined it on the screen? But also notice that the double slit was a cosine, but the single slit is a sine, which means what? They switch roles, right? That's what we said earlier. The equation to find bright spots for the double slit was d sine theta equals an integer number of wavelengths, right? What was the equation for finding the location of the, well, maybe I'll do dark spots for the single slit. Right, A sine, oh, I didn't want to erase that. What's it, beta equals 2 pi lambda A sine theta. Okay? All right, coming back here. So this A sine theta is really what I wanted to spend this first hour emphasizing, that this is the equation to give me minimums. It looks a lot like this one, but this one is where I get maximum. And so really kind of the same thing is going on. I got interference going on. And so to understand why the light spreads out, it is because it's an interference with itself, right? How it adds up. And that's the pattern you're going to get. You are going to get bright, dark, bright, dark, bright, dark. And that's the pattern you saw. And that's what you see in the math. You see bright, dark, bright, dark, bright, dark, bright, dark. Although this one is kind of interesting here. You have a denominator that seems to be increasing. It didn't happen over here. So what does that denominator do? Right. Notice that as you move further and further away, in fact, maybe I should ask, what is beta when you're straight down the middle? 0, right? It's the phase between the first and the last wave. And when you're straight down the middle, the phase is 0. Now, more on that in just a second, because if you look only half at this, you'll go, well, wait a minute, the denominator goes to 0. Yeah, but what does the numerator do? it goes to 0 too. And so you can take a limit of two things going to 0, right? If we do L'Hopital's hospital, there, I like that one. L'Hopital's rule here, okay? And you can take that limit. And we will in just a second. But let's not talk about off-center. Let's go off to the side. And what I'm trying to say is, as you go off to the side, as you go further and further and further off, this last wave becomes bigger and bigger and bigger in phase difference between the first one. And so what ends up happening is this number just constantly gets bigger and bigger and bigger and bigger. And if the denominator constantly gets bigger and bigger and bigger, the over function gets smaller and smaller and smaller, and that's what you're seeing. And I want you to realize you're seeing those two things together. You are seeing the trig function go on, off, on, off, on, off, on, off. But at the same time, the denominator is getting bigger and bigger and bigger. And so as it goes from on to off to on again, when it goes on, it is smaller than it was before. It'll go off again and then go on, but it'll be smaller than it was before. And so sure enough, this is the pattern of what is referred to as a sinc function. Sine of x over x. What's called a sinc function. When you square it, you have this. You have down the center, dark, bright, dark, bright, dark, bright, dark, bright, dark, bright. Dark, bright, dark, bright, dark, bright, dark, bright, dark, bright. And so you have a fringe pattern, and I think you can see that in the trig, but I think you can also see the intensity gets less here. And the last question is, what about right down the center? What about the limit of this as x goes to 0? Yeah, which would be the same if I take, what if I take the derivative of the numerator and the derivative of the denominator? And that, I can take the limit, and it goes to 1. And so, down the center does not get infinite because the denominator goes to 0, nor does the function go to 0 because the numerator goes to 0, but there is a well-defined limit. It's a limit of 1, and that's why, at the middle, what would we get? Just I naught. And so this center part is I naught, and then it goes bright, dark, bright, dark, bright, dark, and each bright is a little bit less bright than the one before. Yeah?
Wait, what is the sine x? What does that come from? Like sine x divided by x squared equals sine squared x?
Sine x over x. Right?
What is the equal sine c squared?
All right. No worries. We'll just lower your grade. So, and this type of function shows up a lot. So I don't know if your education has got you to the point where you call it a sinc function, but this may be a new notation to you. I probably shouldn't have gone this far. Have you guys seen this?
No.
You do? Okay, so you haven't done sinc functions.
But it makes sense, and it's cool that you showed it to us.
Okay, so sinc functions, right? So it wouldn't surprise me if you don't come across it, because there's all kinds of functions. I mean, I know you've come across sine functions and cosine functions, hyperbolic functions, sinc functions, maybe not. How about Bessel functions? We're going to see that before the day's over. Do you know about Bessel functions? Yeah. All right. We won't actually do functions, but we'll mention Bessel functions. So there's another one that kind of at the transition of the end of the level of this class. Because Bessel function shows up after Math 160, right? In 220? Yeah. So again, that's why this book is written at a Math 160 level. So we'll mention all these other ones. So, question? Yeah? Okay. All right. Anyways, I'm hoping we got to the point of this is the single slit. And now, for the grand finale. The grand finale is to say, what would you really see then with a double slit? Because wouldn't a double slit be a single slit intensity pattern and the interference pattern created from here, right? And so, final conclusion of the double slit that we've been dealing with comes out to be this. What would be the intensity on the screen? And so, not a surprise, I have a double slit. And we will make it nice and dark in here again. But if I were to shine the light through a double slit, I guess I would expect to see this. I would get some intensity, call it I naught, down the center. Maybe I'll write the cosine first. But as I moved away from center, I would expect it to be going bright dark and bright dark due to the interference of the two slits. But in addition to that, I would expect it to go bright dark from the fringe pattern or the interference pattern that is created within the slit itself. Now, keep in mind, we did this for the double slit. What happens when you bring the double slits closer together? What happens to the pattern on the screen? They spread further out, right? So the smaller the D, the more they spread. And I'm going to ask you again. Phi was 2 pi d sine theta over lambda. Beta, as we did over there, is 2 pi a sine theta. Which one is smaller, A or D? A's got to be smaller. A's the size of one slit. You can't have the two slits closer together than the size of the slit. Otherwise you wouldn't have a gap between them. So the interference pattern, you will, is the total pattern, is a combination of the two. That's what I want to emphasize. You're going to have them bright dark for two different reasons. One, because of interference within the single slit, and one, because of interference for the double slit. Which one is going to be spread out more? The single slit, what we call the diffraction envelope. If we put these two together, we get to figure 7 here in the book, and like I said, the grand finale of the double slit is to say, what really would you see on the screen? This is the pattern I hope you will see. And I'll turn off the lights here in just a moment and tell me if you do not see it bright in the center and goes bright, dark, but as you are moving over, they will get dimmer and dimmer and dimmer and dimmer and then disappear. Why do they disappear? Well, here is the plot of this very complicated function that is putting together last chapter and this chapter. There is an interference from the double slit, and there is an interference within the single slit, what we call a diffracting envelope. And so your author has tried to draw the diffraction envelope in blue, noting that within an envelope here, it would go bright, dark. And so this bright, dark that are close together is because of the double slit interference. The missing bright, dark pattern over here is because of the destructive nature of the interference within the slit itself. In other words, at that location on the screen, if you got light on the screen from the slits, they would have been constructive, but they're not getting any light. And so you are missing fringe patterns in here. And they have it growing down. You're missing just one. The ones around it are pretty dim, but then they get bright again, and then they get dim, and then they get bright again, and then they get dim. And so this is our complex pattern. Shutting off the lights all the lights, you will hopefully see similar to that. I think that alignment looks pretty good. My double slits start in the center, bright, and then goes bright, dark, bright, and now one's missing right there. And so this is what we call the central diffraction pattern. And then it gets bright again and then gets dim, and then gets bright again and then gets dim. Bright, dark, bright, dark, bright, dark. I might move this just a hair, see if, but it looks pretty centered. I think that's the best. Yeah, we're going to get right about there. Bright, dark, with some missing ones. And so that, like I said, is our first hour. Well, hour and 13 minutes. All right, of what happens to the light as we add together. Yeah.
Is this the new equation for double slit?
So this is the total equation, and that's probably the best way to describe it. This is the total equation. The diffraction envelope, this part of it, we did not do in the last chapter, and so we, had a lot to do here. Yeah.
Are you going to explain why the light changes direction when it goes through the slit?
Oh, why it spread out to begin with?
Yeah.
Let me try this one then. I guess what I really did was just, number one, showed you by example, right? I cut it in. Let me do this then. Which is a little bit of circular reasoning, I realize. But it's at least consistent reasoning is what we like to say. Because let's say, I already assumed that it got smaller, the light spread out uniformly, right? And what did that lead me to? Well, it led me to this diffraction pattern, this one, right? That spreads out. In fact, let me replace inside of here what beta really is. So this would be a pi, an A, sine theta over lambda. And this one down here, of course, I guess would be the same thing. Pi, A, sine theta over lambda. Now, look at this as A gets really small. What is this saying? Or maybe I should have done it with this. A sine theta equals an integer number of wavelengths. This equation is telling me where do I get the first minimum. Fair enough? Let me solve for theta. So the first minimum occurs at some angle that is based upon the wavelength and the size of the hole, right? Let's say the size of the hole is 1/10 of a wavelength. In other words, what happens if A is smaller than lambda? Isn't this greater than 1? There's no solution. What are you really saying? Well, let's go slightly bigger than 1. Let's say A is a hair bigger than lambda. If it was exactly equal to lambda, and you're looking for the first dim spot, the first dark spot, wouldn't this be 1? And at what angle does sine theta equal 1? 90 degrees. So what I'm saying here is if we made a hole, as you saw me do, and you tighten in the screw, and you make A get smaller and smaller and smaller and smaller, what happens to the point of the dark spot? Doesn't it spread out more and 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 more? And if you were to make it A the size of the wavelength, the spreading out would be so much that you would never see a dark spot. You wouldn't even see the first one, because that would be at 90 degrees. And if you make the hole even smaller than the wavelength, you're essentially spreading out the light even more. Anyway, it's not a complete answer, but if I keep doing this in terms of the limit as A getting smaller, what is this equation really saying? That the intensity for a small hole would spread out uniformly. Now again, a little bit of a circular reasoning in that my final result is self-consistent with my assumption at the beginning, okay? But that's how Huygens did it. Now, the flip side of that is we could also remember that these are electromagnetic waves. And this wouldn't be a good time, but maybe in class, since you already took 122, if you remember that last chapter, chapter 34, where we did electromagnetic waves, you can see it in there. That one wave produces another, produces another, produces another. And so at any instant in time, the next set of waves is produced as if that first section is a wave going in all directions with interference. And so it does fit the math from the electromagnetics. But that's not how I did it. So I'll just say that my circular reasoning is self-consistent, but not a complete proof. Yeah. And if you want more of a proof, I'll show you with the electromagnetics. Yeah. Well, anyways, with the time I have left, I hope you got this idea down here that this is the pattern you would see. Because your author throws something else in here. He says, well, what are the consequences of this? Well, what that means then is anytime light, or for that matter, radio waves go into a small hole, they spread out. You probably notice this most with your cell phone, particularly in this building. This building has lots of metal wiring and metal framing. And if I were to stand outside of this building, I can pick up a radio signal real easily. And if I walk about this far in, I still can pick it up. And still pick it up. Kind of pick it up. Not so good. I can get a text message, but I can't use my cell phone. Until I get over here, now I can't use my cell phone or the text message. Why? What's happening? Right, these electromagnetic waves have to go through an opening. This is my opening. Well, not this, but, well, not this. This is cement. But the other walls, they got metal rebar in them, all right? And it's a metal frame. And when the waves go through there, what's going to happen to them? They're going to spread out, right? And according to how much they spread out is based upon the wavelength and the size of the aperture. Now, I pick on radio waves because radio waves are much bigger than light waves. And so if I just had a metal screen or a metal grid, or if I just opened this door here and let the light come in, this hole is so big compared to the wavelength. I mean, that hole's got to be 1,000,000 times bigger than that wavelength. And so how much spreading do I have? Well, about 1/1,000,000th of a radian. I mean, the angle's so small, I'll just do small angle approximation. Right? So there's my spread. 1/1,000,000th of a radian. That's not much. I'm not even going to see it with my eyes. I can just do this. Nope, don't see it. Although, I should point out, you actually can see it with your eyes. If you took a really bright light and you made a nice sharp edge and you look at the sunlight coming down, look down at the shadow. It won't be a sharp edge. There'll be this blurring or this feeding, this bending. But that aside, I'm not going to see it much for light waves, but I am going to see it for the radio waves. So as the radio waves try to come in, they're nice and intense, they hit here and they spread out. Now, as long as I'm close to that, they spread out, meaning they're lowering in intensity. You probably saw it on the wall as I turned it down. Did you notice the intensity was getting smaller and smaller? And so my cell phone can still pick it up when I'm here. Maybe here, but at some point I'm deep enough behind this wall, I don't pick it up anymore. But yet I pick up my text messages. Why?
Because you're receiving instead of sending.
No, it's just I'm receiving.
Because the wavelength.
The wavelength is different, exactly. And so I got a different set of wavelengths here, and I got a different amount of diffraction going on. And if I had a smaller wavelength for my text message, then it would be tighter in and be less spreading, and I can pick it up here. Okay. And there's a lot of other things going on too, so maybe I should be a little bit careful. I take it too far here. But it's why your author then says,
Text messages use the same frequency as calls. They're just simpler.
Yeah, that's why
are they the same frequency?
it's difference in intensity. I thought it was because your cell phone has a weaker signal than power.
Text messages are just simpler. It's like trying to say a letter over the radio or a song.
Okay, fair enough. That was a bad example. See if we can think of a better example.
The difference between light
Oh!
and your cell phone is pretty
Better example, yeah, that was a bad example. AM and FM radio would be a good example. If you, maybe if you go under a bridge, you can still pick up the FM, but you can't pick up the AM. The metal in the bridge blocks it. That was a better example. They are different wavelengths, yeah. So that's a better one. What I really wanted, though, is to stay focused on the optics. So that was probably a bad idea. But, and maybe I should just say sound waves, the same thing. Sound waves are still waves. They, too, would then diffract out. And their wavelength, if you remember when we did the sound back in chapter 17, they're somewhere between here in wavelength. But the point is, what would happen for sound when it went through this door? For sound, the size of that door is roughly the size of the wavelength. So what's going to happen to sound as it goes through that door? It is going to spread out. It's going to spread out quite a bit. And so whereas light waves are small wavelength and do not spread much when they go through the door, that's why if the sun was shining in and I were to stand back here, I could not see the sun. The sunlight rays would come in that way. Now, granted, I could see the light reflect off the ground, but I would not see the light beams turn, and I would say, hey, I could see the sun. But on the other hand, if there was somebody standing outside on that table, and they were making a lot of noise, and I stood back here, could I hear them? Yeah, very easily I could hear them. The sound waves would come in, hit the door, and spread out, and I would get the sound waves, yet I can't see them. And so I do have a spreading out of the sound waves more than the spreading out of the light waves. The physics is still the same, but it's the difference between what is the wavelength compared to the size of the opening. That's my point, yeah.
So if the door was smaller than the wavelength of the sound, then you wouldn't be able to hear it at all?
Well, it's not that you wouldn't hear it at all, but as it spreads out more, and so the door is the size of the wavelength, you could think of this, it doesn't really match the math here, so we need to do something more, but you can still think of this as the sound waves would spread out until you got exactly the size, until the door was the size of the wavelength. Then you might say it spreads out more than that, so actually the sound is coming back at you. But some is still getting in, unless you got really, really small. And so, yeah. So, but there's always just that hair that gets in. Anyways, all of that was to say then this. What happens if you have an opening, like a camera, a telescope, the pupil in your eye, and you're trying to let light come in and get an image of something? What's going to happen to that light? Unfortunately, it's going to spread out, right? And that spreading out is going to make it hard to get the resolution or to get the details of that image. And so here your author is trying to show you this by saying, look, here is the opening. Like I said, this could be a telescope. This could be your eye. But if you have light coming from source 1 and light coming from source 2, and they come into here, he draws what is going to happen on the retina of your eye, or on the CCD of your camera, is that the light would spread out and spread out. And so it's going to make a lot of area on your retina. Now, in this case, he's trying to say that the light would spread out, but these little parts of your retina would be able to pick up the light, and these little parts, and so they're far enough apart that even though the light spread out, you would still say, I've got light source 1 and light source 2. But look at this picture. What happens if light source 1 and 2 are a little closer together? And as they get closer together, they're still going to spread. But something that looks like this, the light coming from source 1 spreads out, the light coming from source 2 spreads out, and what you get in this middle area is an overlap. And so the total intensity you see might just be looking like one blob to your eye. And so what's your eye going to say? What's the camera going to get a picture of? Just say, hey, this is just one source. Twice as bright as just one by itself, but it would not be able to resolve the image. It would not be able to say there are two different sources. I think his next picture does a little bit better job with the map, or with the graph. He kind of plots both of these and says this is what they would look like. If you've got two blobs spread out, your eye would pick up the sum of the two. This dotted line is the sum of the two. So see how some of this blue one gets spread out onto this brown one. And so the overall is a little bit brighter there. You got a hump, if you will. And over here, the same thing, it's a little bit brighter. But because it's a little dip in the middle, your eyes or your electronics would say bright, dim, bright, and you would pick up two different light sources. But as they get closer together, right here is kind of the transition between far apart and too close. Here, they kind of dip down and come back. Here, they are so close that when you add them in the middle, you never see it dip down. And so your eyes are just going to go, one light source. And they are too close. So here's what we like to say in general. In general, they need to be at least this far apart. That is, if you want to resolve this image, you need to make sure that the minimum from one of them is right at the maximum of the other. If they are closer than that, then you don't get really a dip in the intensity pattern. And so this is as close as those two objects can be, and still be resolved by either your eye or a camera, because there's no dip in the intensity. And your eye and your camera just picks up the intensity. Yeah.
So if they were different frequencies, couldn't you separate them?
Oh yeah, if they were different frequencies. But let's say this is, two stars you're looking with a telescope. They're essentially the same stars. They're giving off essentially the same light. You may even put a filter on your telescope and only let one of those many frequencies in. It's not like you can block the intensity from one and the intensity from the other. But when it comes from a telescope, or the source has multiple frequencies, you can't do that. Now, granted, if these two sources were, this one was only red and this one was only green, oh yeah, that'd be real easy, right? I just put up a filter that blocked green and only let red in, and I would see one, and then I would see the other. But that aside, I could not tell if there were two stars. Maybe you notice, I think a good example is a car really far away. If you've ever been in a dark situation, a car really far away, it has two headlights, but when it gets far enough away, you can't see two headlights. You see just a blob, and you see really bright light. Or tail lights if it's going away, so it's not quite as bright. But either way, when it gets close enough, then the angle becomes a little bit bigger here. And so this is what we call the limiting condition, theta. If you're going to resolve these two, theta needs to be either greater than or equal to lambda A. If that angle's smaller, you're not going to be able to pick up two objects. Yeah.
There was a professor at Ventura that told me he used to work on the Keck.
Oh, okay.
And they had a way to resolve that with post-processing.
Oh, okay.
Separate the images even though they were overlapping.
Yes, because then what you do, right, if there's an assumption to be made, but yes. And you can see it in the math here. I mean, what if I really did get this? if I look carefully at this intensity pattern, it probably does not follow a sync function. So like you're doing in your linear algebra class, you could take the pattern that you have, your basis set would be sync functions. How many sync functions do I have to add together to get the pattern? And that's your post-processing. And then you would say, all right, it took 3 sync functions, so I must be looking at 3 stars clustered together in order to get that. Because your assumption behind that is you would get a sync function. But it's not an unreasonable assumption, so yeah.
You could probably do something with the composition of the stars too, if there was a difference between the composition and then the wavelengths of the light they emit based on that.
Well, right, and that's what he was saying here. Now, I was saying if they are all the same type of stars, you couldn't because they're giving off the same spectrum. But if you knew one was significantly hotter than the other, you could probably then take a picture of just, say, in the X-rays. And you wouldn't pick up the other one. And you would only be picking up that one because it's, you know, in the X-rays. Yeah. So, yeah, I don't want to leave like there's not more we can do. Like I said, we got 107 years of physics still to learn here, right? So there is a lot of other things. But in this simple model here, I couldn't tell them apart. And that could be good or bad. Like I said, if you're trying to pick out 2 stars with the telescope, this is probably a bad thing. I think your author gives an example of the first discovery of the moon of Pluto. I think it's Sharon. And the first discovery, and he shows these just 2 blobs. And the original photographs, we never knew that Pluto had a moon, you know. And we're lucky even to find Pluto, you know. I think Pluto was discovered, what, 1930 or something like that. So they got a picture of it, but it wasn't a significant resolution that you could tell there is something going around it. There's 2 blobs there. And of course, the ones your author shows you, he shows you a really good high quality one of today, and it's very clear. Here's Pluto, here's the moon, Sharon, yeah, way over there. And so we can see it. But I would like to do the reverse of you. You probably notice more with all your electronics. I mean, here's what you would like to do. You would like the little pixels to blur together in your eye. You want them to blur, right? You don't like to look at a screen that has pixel, 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 right? On, off. And so the idea is to get those pixels close enough together so that when you're holding it here at this distance, they will blur together. Or if it's a TV screen, since a TV screen is usually further away than a handheld device is, you can make the pixels farther apart. And usually, and they blur together. And so your resolution is usually a lot higher and needed to be a lot higher on those things that are close compared to those things that are far away.
Would this have anything to do with like a myopia, or would your eye have like a smaller angle that it could handle if you were like nearsighted or farsighted?
Not to say there are not other issues going on with the eye. But not this. Right. This is just pure diffraction. And again, so maybe I should just get away from the eye and say this is a telescope or a camera. This is a camera. Just I'm just trying to see if I can take a picture of the individual stars or the individual trees on a distant mountain. And they're going to blur together. Well, the last thing then is polarization. And so let's see how much we can do on polarization. As I was saying here is that the polarization of light is something that we're not as acquainted with optically because we don't pick it up with our eyes. It's probably best to remind you of our light waves and what they would look like if you could see a wave traveling. Your author does this again in figure 24. He says, remember this. This is what a light wave would look like. It's an electromagnetic wave. And so when we draw a wave, and we say this is a light wave, what are we drawing here? Yeah, we're drawing the electric field. And so in this case, I would say the electric field at this position is pointing up. At this position it's pointing down, and then up. And in fact, it's always up It's just here it's up smaller, or perhaps it's down, and here it's down but smaller. But the point I'm trying to make is the electric field will be in a certain direction. And that's what we mean by polarized. Light is polarized. And so as the light goes to your eyes, and it comes towards you, it has to be generated. It could have been generated so that the electric field was oscillating this way. And if it does, I would call that vertically polarized light. Now, my eye doesn't recognize that, because if I were to send a light that is polarized this way, the electric field, I would call it horizontally polarized. And it would go to your eye, and guess what? You're going to see the same thing. In fact, believe it or not, that's what this laser was doing. You probably wouldn't even notice if I just shine the laser. This laser is built so when the light comes out, the electric field is vertical. And it's going up and down. If I were to rotate the laser 90 degrees and do that, now the electric field's horizontal. And your eyes don't pick that up. They don't detect that. So you're like, well, what's the difference? Well, there is something different physically. There's the direction of the electric field, but your eyes isn't going to pick it up. But I do have some devices that could pick it up. Yeah.
Quick question. So maybe, I know for like certain like polarized sunglasses, they put all the polarity the same way. How come that makes images clearer?
Good question. And I hope to answer that within a couple minutes here. Right? Yeah.
You want to discuss about the electric field. What about the magnetic field? Does it change at all?
Well, the magnetic field would have to be perpendicular to the electric field. So what I'm pretty much doing here is talking about the electric field, hopefully emphasizing that there is always a magnetic field. I'm just not drawing it for simplicity.
Okay.
Yeah, but it's there. And so we could label things from the magnetic field. We just like to do it from the electric field. That's, tradition. But you can't have one without the other, right? Now, let's add to this complexity. This is why your author gives this picture here, and then he follows it with this picture, and he says, all right, if the electric field is going up and down like it is now, then we will represent it with a vertical line saying that's the direction of the electric field. He doesn't show one up here that's horizontal, but I think you might guess, what if I were to hold the laser beam this way? Now, then I would draw a horizontal line. What's this?
After it goes through the slit.
Right. This is what we would call then unpolarized light. Now, what do we mean by unpolarized light? Well, remember, let's take any light source. I just happen to have a bright light. But it could be this light. It could be the sunlight. It could be a fire. It could be a candle. Most of the light that we create in this world, unless we do something fancy with it, is what we would call unpolarized light. What we mean by that is if this is my light source over here, so that's the sun, and I'm over here on the earth, I get light from all those different atoms. So one atom is making the light go this way. Another one is going this way. Another one is going this way. Another one this way. Another one this way. Another one this way. So when I stand back here, any one ray is, of course, polarized. But I don't get just one ray. There are billions and billions of molecules and billions of light rays then that are all adding up together. And so the best way to describe that is to say, hey, it is unpolarized. And this is how we kind of draw unpolarized, kind of saying, look, we've got one going this way, we've got one going this way, we've got one going this way, we've got one going that way, and that way, and that way, and that way. And we just draw this big hash mark here and say, okay, well, I shouldn't say hash mark. That's a whole new term that you guys use for the old pound symbol, right? In fact, if I say pound symbol, do you know what that is? A hash mark, right? Okay. The hashtag. All right. Anyways, but this is these vertical lines here. Now, The reason I put this on the screen here and going to do as much as I can before.
But that's an infinite number of directions, right? Axes.
Ah, come on, machine. It's not working. Lower screen. Lower. Danggummit. All right. Change. Off. No, I'll just use a whiteboard. All right. I was going to lower that big screen, but this will work. I think you'll see it here on the whiteboard. But back to what I was trying to say here. If I just have a bunch of light coming from a bulb, and that's what I have right here, a bunch of light coming from a bulb, that bulb has a filament. There are billions and billions of molecules. I would say this light is unpolarized, meaning it is making some of the light horizontally, some is vertically. Well, this little sheet, if you could see it on a molecular level, is made out of molecules that are very long and thin. Now, imagine, if you will, metal poles, long and thin, like a prison. Hopefully you're looking in, not out. But here's a prison, right? And so you got all these metal bars. And there's a rope that goes down there. If I were to shake the rope vertically and make waves, wouldn't they go through the metal bars? But if I were to shake the rope horizontally, what would happen when they hit those bars? They would get blocked, right? They would stop. They would hit and turn into heat, right? They would be gone. They wouldn't go through to the other side of the bars. Well, let's take that analogy to light. If I take these molecules that are long and thin, they will let light go through when it moves in one direction, but not the other.
Does that mean some get through because they get it?
No, well, you're talking about a standing wave. There's no nodes here, because when I make a hump, it's moving. So yeah, there's no nodes here. Yeah.
But wouldn't that kind of just do what we just did, where you have small slits?
Yeah, well, then they would spread out, but these aren't infinitely small.
It's kind of the same idea. You said lots of little slits, right? It comes through, you got a little gap.
Not.
It just comes kind of through a gap, and then all of a sudden it just stops at this time, then another time the thread spreads out like a wave.
No, because they're not really slits. I mean, this is one solid molecule where a long molecule here is then hooked to a long molecule here. There is no opening in between them. Don't take my analogy too far. I better hurry. What did you notice right away? Got darker. Why? How much darker?
50%.
I blocked half of them, right? And so, oh good, I'm glad I could use this, because I really wanted to use this. If I were then starting with unpolarized light, this is what this image is. Oh, this image.
Clock's running.
All right, so if I were to start with unpolarized light, and then I would hit this polarizing filter, what do I get on the other side? Okay, number one, I get polarized light, right? And number two, I get half of the intensity. Now, he doesn't write half the intensity here, so maybe I'll put that over here on this part of my board. But I would get unpolarized light going through a Polaroid sheet with the molecules in this fashion. What I would get if I started with an intensity of I naught, and over here I would get intensity number 1, I claim that I would get half of it. And so I would get half the intensity, but more interesting for me is I would now have polarized light. And that's my way of getting polarized light for you.
Why is it half if you're blocking most of the ray? Only letting you do that?
Not most. Remember, vectors. If I had a vector, if I had a ray that was at an angle, that can be thought of as part of it is horizontal and part of it is vertical. So it doesn't stop 100% of the ray that is at 45 degrees. It stops just the component that is horizontal, but lets part of it through. So all the rays that are horizontal get completely blocked. All the ones that are vertical get all the way through. The ones at 45 or 30 get partially through. Right? And so there's some at 30, but there's some at 60. Right? Well, again, in the short time we have left, I will then say, what happens if I take a second polarizing sheet, I place it on, it will get a little bit darker just because I get reflections off of them. But at this angle, I am pretty much letting all the same light through until I do what? What if I rotate it? Rotate it. Rotate it. Rotate it. And when I get right there, I have blocked all the light that I get through. And in the short time I have left, I will pass these around. If you want to hold them up and then cross them, you will see dimmer, dimmer, off. They're cross-polarized at that point.
Put it on there. Third one.
Yeah, I'm going to put a third one on here. Hang on. See how much time we got. But what I want you to do, if they get it to you, is try this with your LCD screens. They used the polarized light. The light comes in, gets polarized on the way in, then it either gets rotated or not rotated as it comes back out through the polarizing sheet. If it got rotated, then when it comes out it would get blocked. That's what all the dark writing is. If it doesn't get blocked, that's where all the shiny stuff is. To convince yourself, just hold this in front and rotate it. You will see how polarized that light is as you turn it in front of your screen. And so here, well, here's the two together. Grab your calculator, or your watch works really well too, but your watch is using the polarizing light. I mean, your display is. Watch this one. Let me change to, well, that's almost a white screen. What happens if I put this in front of that white screen?
Purple, I have no idea.
What if I rotate it?
Not expected.
Do it again.
Right? So,
Turn it clockwise.
so the engineers have built this with the idea that three different lights are coming out, red, green, and blue. And so they can combine them together. They've actually designed it here for the green to be horizontally polarized. It has nothing to do once it leaves the monitor, but so they can control it in there, they have it polarized in that way. Whereas the other two colors, they have polarized in a vertical direction. And so what you see is the reds and the blues here. And so you see this magenta.
The projector has
Green.
the red and the blue
Right.
on one axis and the green polarized on the other.
Right, right. And so they come out that way. Our eyes never detect that the green is polarized horizontally and that the red is polarized vertically. But obviously you can see it here. Now again, in the short time I have left here, notice then that the intensity that comes out from the second Polaroid, intensity number 2, would be what? Yeah, it's not just an easy, half or 1/3. It would depend on how the second one is aligned with the first one. And so if I started with this first one vertically, and the second one then rotated an angle theta from that, as Zippy, you were pointing out here, how much would I get through? Well, if the original one polarized it in a vertical direction. And then I rotate the second one. The part that gets through would be the cosine of that piece. So the electric field would be, how much electric field do I get here times cosine of that angle? Now one more step. The intensity is the electric field squared. So to get the intensity on the other side, I would have to have cosine squared. And so on the other side, I would have the intensity that came in. Maybe I should write it as intensity number 1 times cosine squared on the other side. And what if it went to a third? And a fourth? And a fifth? In fact, this was your suggestion. Why don't I put a third one in here? Watch what happens here. Again, looking back on this whiteboard here, here's what I have. I have the projector, so here it is, the original intensity of the light right there. And then I put my Polaroid sheet here. That cuts out half of it right now. Then if I take that second polarizing sheet right here, okay, and if I just put it this way, it should let 100% go through because cosine is 0. And as you saw, as I rotate it, the intensity goes down and down and down and down. And if they're at 90 degrees, I mean, what is cosine of 90 degrees? Yeah, 0. So I get 0 intensity on here. But what if there was a third one? Say in between here. This is always kind of weird to see. I mean, how much right now, if these two are 90 degrees apart, how much light gets through? None, right? But what if I were to put, and maybe I should change my picture to match what I have right there. What I have right now is this one at 90 degrees to the first one. What if I were to put one here that is at some angle? Wouldn't some light get through this first one? Of course, it would also then change the polarization angle. So then what happens here? Some actually gets through. I mean, the intensity on this side then would be, what did I start with way over here? First cut in half as it went through this one. Then cosine squared of the first angle. But then that is reduced again by cosine squared of the second angle. But neither one of those is now 90 degrees. And to me that seems like always kind of weird. Okay, wait a minute. I had two sheets where nothing gets through, right? And I put another sheet in between them that does nothing more than absorb light. But the real key is it rotates the light so that the second one really can't block it. And so if I take a piece of, it's a little arrowhead made out of the same material, cut out, and I were to lay this in at 45 degrees, you will actually see some of the light get through. Or one of my favorite is our high-tech expensive toy. Okay, these can holders made out of plastic. Now, plastic are again these long molecules. More than that, as I pull and stretch, taking the cans out of here, I twist those molecules so they were probably in a random direction when it was manufactured. There was no intent of making the light polarized. But as I came along and pulled out my cans of juice here, I probably put stress and I twisted the molecules. And so this is probably acting a lot like that piece in the middle. And it will rotate the light. Better than that, it'll probably be polarized based on whatever molecule I stretch, because this is just a random, it's got molecules of different sizes. So the reds and the blues and the greens will probably twist more. So what happens if I put that in between my two polarizing sheets? What will I see? Yeah, I will see the light being polarized, and different colors are polarized based upon different stresses that were added to my plastic. This is an absolutely wonderful experimental toy when it comes to building models and saying what are going to be the stresses on a bridge, on a building. And this is supposed to be a model of a cathedral. And so they're mimicking an old cathedral and saying, where are the stresses in the rocks here? And what they've done is exactly what I'm showing you, is they have put two polarizing sheets, one behind the other, and they built the model out of plastic, and then put some artificial weights on there to see how they would twist, and you begin to see how much they twisted. And these places here where the gradients of the colors are really close together, it means you go from one molecule to another molecule, it's twisted a lot, meaning there's a lot of stress on those molecules right in there. And so we can clearly see where there is and is not stress. And so that's what I was saying earlier, you mechanical people, don't think you're ever getting away from this optics. I'm sorry. It is such a useful tool in a lot of different ways. Well, one more, it looks like all we'll have time for. How about these? What do you notice? What if I rotate it? What do you notice? What you hopefully notice is these glasses have polarizing sheets in them, and they are different. They are 90 degrees apart. Why? How do you see in 3D again? What did we do 2 chapters ago? Yeah, the light that goes to one eye is a little different. The pattern is a little different than the other eye. So, in order to make three-dimensional movies, 3D movies, we have glasses that have polarizing sheets built into them so that you can project 2 images on the screen. One you see with your left eye, so this sheet only lets that light through, and one you see with your right eye. If you're ever in a 3D movie, take your glasses off. I love 3D movies, but I have a hard time watching the whole thing. I'm just constantly looking at the glasses and pulling them off my head. Because when you pull them off your head, it will look blurry. You will see 2 images. Exactly. And then as you hold them up, you can compare them. Or if you play games with your LCD screen here, or with your friend's glasses, and you play with them together. Well, wish we could do more. I guess that's all we did. Your polarizing sunglasses are awesome because reflected light off a surface tends to be horizontally polarized.